Okay, so what can go wrong? Well, actually, quite a bit. Hypothesis tests are so widely used and so widely misused that issues involved are discussed in their own chapter. So in chapter 21, we're going to talk about all kinds of issues with hypothesis tests. So be prepared for that next time. There are a few issues that we can talk about already, though. Don't base your null hypothesis on what you see in the data. Think about the situation you're investigating and develop your null hypothesis appropriately. Don't base your alternative hypothesis on the data either. Again, you need to think about the situation. Actually, these things should be determined before you gather your data. Don't make your null hypothesis what you want to show to be true. You can reject the null hypothesis, but you can never accept or prove the null. That's why the alternative is what you think is actually going to be true. Don't forget to check the conditions. We need randomization, independence, and a sample that's large enough to justify the use of the normal model. What we'll need from this sample is for the expected number of successes and the expected number of failures under the null hypothesis to be at least 10. Don't accept the null hypothesis. Never ever say that. All you can do is fail to reject it. Now, if you fail to reject the null hypothesis, don't think that a bigger sample would be more likely to lead to rejection. That's not necessarily true. Each sample is different, and a larger sample won't necessarily duplicate your current observations. All right, let's look at examples. Let's look at exercise 12 on page 477. In the 1980s, it was generally believed that congenital abnormalities affected about 5% of the nation's children. Some people believe that an increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. That's a big hint for your alternative there. A recent study examined 384 children and found that 46 of them showed signs of an abnormality. Is this strong evidence that the risk has increased? So that is what is believed to actually be going on. So that is telling us about our alternative. All right, so first thing we do is write appropriate hypotheses. So our null is that things are the same, okay? Things are just like they've always been. The true proportion of children having congenital abnormalities is still, as it has been historically, 0.05. Our alternative is that P is greater than 0.05 because if you look at this, it says people think there's been an increase in the incidence of abnormalities. Is there strong evidence the risk has increased? So we know it's one-sided and greater than. Now we're told to check the necessary assumptions, and actually we're going to check the conditions so we can make the assumptions. Simple random sample. N greater than 10n. Remember, you want the population to be greater than 10 times the sample size. So even if there's an issue with independence, it's not going to affect the proportions that much, and we can still do our calculations. In success failure, we want to make sure that we expect there to be at least 10 successes and 10 failures if the null hypothesis is true. All right, it's not stated that we have a simple random sample or a random sample at all. We will proceed with caution, understanding that our methods make sense only if the 384 children are a representative sample of all children in the nation. If they aren't representative, then this makes no sense to actually generalize to the whole nation. Population greater than 10 times sample size, there are more than 10 times 384, 3,840 children in the nation. Success failure, we expect N times P naught equals 384 times 0.05 equals 19.2 successes, and we expect N times Q naught 384 times 0.95. We get that by doing the 1 minus 0.05. And so that's 364.8 failures, both of which are greater than 10. So our sample size is sufficiently large. All right, we want to perform the mechanics of the test. What is the p-value? All right, p hat is 46 over 384. It's 0.1198. The p-value is the probability that we would get a sample proportion, our p hat, of 1,198 or larger if the true population proportion P is 0.05, our hypothesized value for P. To find the p-value, go to Scratchpad on your calculator, press Menu, and choose Statistics. Under Statistics, choose Stat Tests, and choose one proportion z-test and enter the values requested. So you're going to enter that P naught is 0.05, X is 46, and N is 384. And the alternative you want is the greater than one, because that's what we've chosen, and the way it appears on your calculator is proportion greater than P naught. On the next slide, I will show you how to write up an answer like this. All right, you need to declare what kind of test you're doing. The only one we know how to do right now is the one proportion Z test. It's not a big, momentous thing at this point, but later on, that's going to be the big thing, is picking which test you need to do. I will conduct a one proportion Z test. Now I'm going to report what I get back. Z equals 6.28. That means that our observation is 6.28 standard deviations above the mean. That's pretty surprising. Well, our p-value is about 0. It's 1.75 times 10 to the negative 10. So that means it's extremely unlikely to happen if the null hypothesis is true. Explain carefully what the p-value means in context. If the abnormality rate has not increased, if it is still 0.05, so we're saying if the null hypothesis is true, then the probability of observing at least 46 children with abnormalities in a sample of 384 is approximately 0. So what's your conclusion? Well, due to our low p-value of pretty much 0, we reject the null. These data indicate that the rate of abnormalities is now greater than 5%. Do environmental chemicals cause congenital abnormalities? We have no clue what might the cause be. We just know that we have evidence that the rate of abnormalities has increased. All right, let's look at another example. On page 479, we're going to look at exercise number 30. A startup company is about to market a new computer printer. It decides to gamble by running commercials during the Super Bowl. The company hopes that the name recognition will be worth the high cost of the ads. The goal of the company is that over 40% of the public recognize its brand name and associate it with the computer equipment. The day after the game, a pollster contacts 420 randomly chosen adults and finds that 181 of them know what this company that this company manufactures printers. Would you recommend that the company continue to advertise during Super Bowls? Explain. Okay, so we've got to do everything. We've got to remember to do the hypothesis, everything, without being prompted. So let's do our null, and then let's do our alternative. So our null is p equals 0.40, where p is the proportion of the population that recognizes the company manufactures printers, not of the sample, of the population. The alternative is that p is greater than 0.4. Why? Because the goal of the company is that over 40% of the public recognize its brand name. Okay, so if we have evidence that is the case, then they want to continue their advertising campaign. If we don't have evidence that that's the case, then we're going to have to recommend that they stop. We will conduct a one proportion Z test if the conditions are met. So let's think of simple random sample, n greater than 10n, and success and failure. All right, the problem states that the sample was chosen at random, so we're good there. There are more than 10n, 10 times 420, 4,200 adult Super Bowl viewers. Success failures, we expect n times p naught equals 420 times 0.4 equals 168 successes. And I should have n times q naught there. That's going to be 420 times 0.6. Remember, q naught is 1 minus p naught, so 1 minus 0.4 is 0.6. That gives us 252 failures, both of which are at least 10. All conditions are met, so we will conduct a one proportion Z test. All right, so we get out our calculator, we go to stats, we go to the hypothesis test portion, we pick one proportion Z test, and we put in our information, and we get Z equals 1.29, and we get a p-value of 0.1. Now that's just really on the bubble there. I would consider that large. If you report 0.1, anything between 0.05 and 0.1, if you report that, that's kind of in a middle area, and unless we've established a cutoff point for the p-value ahead of time, and we'll talk about that later, anything between 0.05 and 0.1 depends on how you interpret it. I'm interpreting it as large. Due to our large p-value, we fail to reject the null hypothesis. These data do not provide evidence that more than 40% of adults recognize that the company manufactures printers. Why? Well, some happens 10% of the time. That's not necessarily super surprising. It's a little unusual, but remember, they're spending tons of money for these Super Bowl commercials, so I would need more convincing evidence than something happens 10% of the time if the true proportion is 0.40. And really, in that, it also includes or smaller. Okay, that's all included, even though it just is written equals. It's really less than or equal to for that null. It's just standard form to write equals to. So that would not be enough to convince me. These data do not provide evidence that more than 40% of adults recognize that the company manufactures printers. Thus, based on these results, I would not recommend that they continue to advertise during Super Bowls. Okay, guys, that's it. I will see you in class and get you started and let you do some practice on some rounds and answer any questions that you have. Y'all have a good day. Bye.